Section 10. Now we move into the interesting part of the course, which has to do with inference. How to use statistics in a practical way. To recap, the last few sections, 7, 8, and 9, have been about the theory of statistics. That is to say, you know the rules, you know the governing principles, you know the broader realities, the parameters, in a word, and you're about to do a sample, and we're looking at the probability that it's this, that, or the other. The pattern of randomness of a sample that you're about to do. So we looked at the sampling distribution for various types of statistics. Now what we want to do is throw that into reverse. Remember that these sections are still the world of probability. You know the rules, the random thing is in your future, what's the probability that it's this, that, or the other? In that sense, it's relatively straightforward. But now as we move to inference, the practical use of statistics, we find ourselves with a different vantage point. We don't know the rules, we don't know the governing principles, we don't know the broader realities. You don't know whether a coin is fair. How could you? How could you possibly know whether 1/2 of all possible flips of a coin would come down heads? How could you possibly know the average height of everybody in the world? How could you possibly know what proportion of people in the world are left-handed? You don't. So in the real world, you don't know the rules, the broader realities. You don't know the parameter. You don't know the population fact, because populations, by definition, are too much to have knowledge, data about. But what you do is you pick a sample, hopefully a representative sample, but you've got no way of knowing, and you get the corresponding parameter. The height of the people, the average height of the people you do measure, the proportion of flips of the coin you actually did that landed heads, and so forth and so on. And from that you make conclusions about what's going on in the real world, right? I flipped the coin 1,000 times and 485 of them were heads. It's plausible that it's a fair coin. I picked out 1,000 people from the world and 11% of them were left-handed. It's not plausible that half the people in the world are left-handed. Things of that nature. So making real-world conclusions from the sample that you happen to have. Now what you've got to bear in mind is, number one, because this is probability done backwards, inference is probability done backwards, it's very hard to think about properly. Number two, what you're working from is random. So you always want to bear in mind that you could just as easily be working from a different sample. You could just as easily have a different statistic. Anything you conclude from 100 flips of a coin has got to take into account that if you did a different 100 flips of the coin, you'd probably be working with something else, and so forth and so on and so on. It's no good happening to get 60% of the people you polled saying they're going to vote for so-and-so if the next time you pick 100 people, you could get 40% of them saying they're going to vote for so-and-so. So this is the logic of the sampling distribution. Before you can get any knowledge out of what the statistic for a sample of this size allows you to conclude about the population, you've got to understand the pattern of randomness, right? Which is what we've just got done talking about. You've got to understand the sampling distribution. Before you know what 100 flips of the coin allows you to conclude about the coin, you've got to know what any old random 100 flips of the coin were likely to be, right? So this is the trick of inference. You have to reason backwards. You've done the sample. It used to be random. You've done the sample. You've got what you've got, but you could have gotten something else. So in that sense, the random thing is in your past. Randomness in the past is always philosophically tricky to think about. But the bottom line is you did the sample. You got what you got. It's not going away, but it could have been something else. And if you did it again, it would be something else. What does that allow you to conclude about the real world? Inferring things about the broader realities, the population, the parameter, from what the statistic happens to be. It means, as we said in section 7, that you never want to say that the parameter is probably this or that. We slip into this lingo informally, and I'll do it again because it's the easiest way to think about things sometimes. But strictly speaking, there's no probability of the parameter being anything. There's no probability that the coin is fair. It either is or it isn't. You can't repeat with a different all possible flips of the coin and get a different answer. There's nothing random about it. There's nothing random about the average height of everybody in the world. It is what it is, whether you ever know it or not. You can't repeat with a different planet Earth and get a different answer. So this is what makes probability tricky to think about. The basic logic of confidence intervals is relatively easy to understand. The thing you don't know is probably close to the thing you do know. But again, strictly speaking, there's no probably about a parameter. So we have to be a little bit careful. It's okay to slip into it just as a way of understanding it. But you always want to bear in mind that it's not about what the parameter probably is. It's about what you were probably going to get in your sample. So although we can say informally that the parameter is probably close to the statistic, it would be more technically accurate to say that we were probably going to get a statistic close to what the parameter is. We were probably going to get a statistic close to what the parameter is. Therefore, we're confident that the parameter is close to what we happen to have. So with all that in mind, let's tackle section 10. You will find, if you look at the titles here, for instance, you will find that this is very redundant. Now, again, I think this is the point that was eluding me in a previous video. I was trying to think of it, and then it slipped out of my head. And if I keep talking, it will again. This is the thing you want to remember, is that, and sure enough, it's gone. So what was I going to say there? Well, it'll come to me. So anyway, confidence intervals. Oh, yes, that was it. You can either make this work for or against you. You're going to find that this neck of the course, this latter third of the course, so pretty much everything we're going to do for the next several sections, is very repetitive. It's the same ideas over and over and over. With minor variations. I mean, again, look at the chapter titles. Confidence intervals, hypothesis tests. Confidence intervals, hypothesis tests. Section 14, in fact, is more hypothesis tests, and so is section 15. So it's very redundant. There's only a couple of major ideas going on here, confidence intervals and hypothesis tests. Also, like I said, if we've done our jobs properly, then the math has been gotten out of the way in sections 7 to 9. So the math is not a major obstacle at this point. To the extent that you're comfortable with sections 8 and 9 at this point, you're not going to find a lot of major mathematical obstacles here on in. It's pretty straightforward and a lot of repetition of what we've already been doing. The problem, as I say, is understanding statistics properly. It's more of an issue with hypothesis tests than it is with confidence intervals. But even with confidence intervals, you want to understand them properly. So, with all that in mind, this is either an opportunity or a problem, depending on how you look at things. You're going to find that the next several sections are all very similar to one another, which can be a big point of confusion for people. You know, as you look back on these last few sections coming out of, say, section 15, it's the same thing over and over again, and that can be very confusing. But what you want to do is you want to make it work for you rather than against you. It is not a lot of new ideas. It is simply every possible combination of 2 or 3 major ideas that we've already talked about. One of those ideas is the concept of confidence intervals. One of those ideas is the concept of hypothesis tests. One of those ideas is the pattern of randomness for p hat. Another of those ideas is the pattern of randomness for x bar. And then basically it's just putting them together in every possible combination. So if you can get the idea of confidence intervals down, then everything that we do in all of our confidence interval sections is going to be variations on a theme. And again, if you can get the idea of hypothesis testing down, then everything we're going to do in our hypothesis testing sections is again going to be a variation on a theme. So we'll talk about how to organize all this in your head after we've done a few examples in various sections. But if you can make it work for you, then there's not a lot of new ideas to take in. It's just a lot of different combinations of old ideas. If it's not working for you, then you're going to be very confused because we literally seem to be doing the same thing over and over again. And there's a reason for that. We are. Anyway, there's an overview of some of the obstacles coming up. They're not really mathematical. The only two major obstacles are understanding things properly. Well, once you're comfortable with the old stuff, the only two major obstacles are understanding things properly and getting over or making it work for you, this sense that we're doing the same thing over and over again. Because really we are. So with all that in mind, let's tackle section 10, which is our first go-round at this. So in section 10, we're going to take confidence intervals rather slowly, and then we'll speed it up a bit when we redo confidence intervals in some of the later sections, because it is just variations on a theme. So, for the sake of argument, now, while I'm here, the way this is laid out is that sections 10 and 11 are the categorical scenario, the p-hat. Yeah, every time you pick, you get a yes or a no, a success or a failure. In other words, they're based on section 8. And then section 12 and 13 are the X-bar situation, the average of numbers situation. So they're very much based on section 9 in exactly the same way. So the formulas are a little bit different, but the logic of what we're doing is very repetitive. And then 14 and 15 are going to harken back to 8 and 9 again, respectively. So it is very redundant and repetitive. So in sections 10 and 11 in particular, the one we're in at the moment, section 10, we're dealing with the yes-no scenario. We're dealing with the p-hat proportion of successes type scenario. And again, I told you that when we get to practical statistics, the proportion of successes is more important than the number of successes for reasons we've talked about. But it does mean that the numbers are very small, right? Proportions on their worst day are 0 point something, unless they're all yeses, in which case it's 1. So for the sake of argument, let's suppose that we have a vat filled with millions of jelly beans of all flavors, nicely mixed together. Thoroughly mixed together, so that basically any handful that you pull out is effectively a simple random sample. We don't have that to worry about. It's not like the licorice is gravitated to the bottom and the lemon is gravitated to the top and so forth. They're all mixed together, so that any handful you pick out is basically a simple random sample. Millions of jelly beans mixed together in a huge vat. Suffice to say, far more than you or I could ever pick out. Any bunch of jelly beans that you and I could actually examine is insignificant compared to what's out there, right? I mean, you could take a sample of 1,000 jelly beans, and that's a lot of jelly beans to examine, but it's still insignificant compared to the whole of that, right? So, as always, samples don't take a bite out of populations. That's what makes them samples, and that's what makes the math something we can cope with. So millions and millions of jelly beans of all flavors mixed together, and let's let lowercase p be the proportion of jelly beans that are licorice. Or probability being what it is, the probability that you get a licorice when you pick one out, right? So obviously, in the real world, we've got a huge vat of jelly beans with them all mixed together, then we don't know what proportion of the jelly beans are licorice. And let's say, for the sake of argument, that it's a nice opaque vat with a cover on it, so that we have absolutely no visual impressions whatsoever as to what proportion are licorice. A sealed vat, we've got no way of looking at it. We'll just reach in blindfolded, open it a crack, reach in blindfolded, pick out some jelly beans and look at them. But we have no visual impressions as to what's going on with the vat, for the sake of argument. They might all be licorice, or none of them licorice, or anything in between. For all we know, every jelly bean in the vat is black and P is 1. Or there is no black jelly bean anywhere in the vat and P is 0, or anything in between. So that'll be important a bit later. We have absolutely no visual impressions whatsoever. This is a totally hypothetical vat of jelly beans, and the proportion of licorice might be anything between none of it and all of it. Now what we'll do is we'll take a simple random sample. Again, if they're nicely mixed together, then effectively any 100 that you pull out is a simple random sample. But We'll say it's a simple random sample of 100 jelly beans. We'll pick out and examine 100 jelly beans. And if the opaque vat is really going to bother you, we'll say that the jelly beans are physically identical and that we're going to eat 100 of them and we can tell by taste what kind they are. But anyway, we pick out 100 jelly beans, and for the sake of argument, 40 of them are licorice. So that's what we know. Now again, what can we conclude with certainty at this point? I've hinted at this before. I'm sure I made the Indiana Jones joke about if it's certainty or after Dr. Tyree's philosophy classes down the hall, so to speak. But at this point in time, we know two things. If you take a simple random sample of 100 out of millions and millions of jelly beans, and 40 of them are licorice, then at this point in time, we can conclude two things. What do we know for certain? Well, we know for certain, unless our eyes deceive us and all that, we know for certain that somewhere in the vat there were 40 licorice jelly beans. And somewhere in the vat there were 60 jelly beans that were not licorice. And that is the extent of what we know. Now again, I think you can learn an awful lot more in a course like this if we occasionally resort to a little bit of sarcasm. Because if it's certainty you're after, then you always want to bear in mind that there's very little we can conclude from a sample under any circumstances. So you always want to be very careful about what you conclude. At the end of the day, we're just playing the odds. 40% of the jelly beans we looked at were licorice, therefore probably about 40% of the whole vat is licorice. The rest is detail and some philosophical cleanup. Again, technically there's no probability of P being anything. It would be more to the point to say that we were probably going to get something close to what P is. So we're confident that about 40% of the vat is licorice. The rest is just mathematical detail. So as you become confused by the formulas that follow, remember that confidence intervals are not that confusing of a concept. The parameter that we don't know is probably close to the statistic that we happen to have. Or if you want to be a little bit more technically accurate about it, we were probably going to get something, our statistic probably was going to be close to what P actually is. But the thing you don't know is probably close to the thing you do know. So 40% of the jelly beans we looked at were licorice. Best guess, only guess, 40% of the vat is licorice. But again, that may or may not be true, and it may be very far from being true. Why not be a little sarcastic about it? What can we conclude for a fact? Well, let's suppose, pretty much nothing is the answer, but let's suppose that for the sake of argument, something cosmic, no, it is a simple random sample. The upside of that is it's probably representative. The downside of that is there's a small probability it may not be representative. You don't know. Bear in mind you have no idea whether this is a typical sample without knowing what P is. And if you knew what P is, you wouldn't be doing the sample. So having picked 100 jelly beans and gotten 40 licorice, we have absolutely no perspective. Without knowing the thing that we're doing this to find out, we have absolutely no perspective on whether this is a typical sample or the most unusual sample there ever was. But what do we know with certainty? Somewhere in the vat there were 40 licorice jelly beans, and somewhere in the vat there were 60 non-licorice jelly beans. Okay, devil's advocate. What if through some sheer cosmic fluke, I mean randomness, not bias, just plain old randomness, what if through some sheer cosmic fluke, again, not because the licorice is toward the top, they're all nicely mixed together, not through bias, but simply through some random cosmic fluke, what if we have picked out the only 40 licorice in the entire vat? 40 out of millions. Well, what's 40 divided by millions? Practically 0. So if we have just picked out the only 40 licorice out of millions and millions in the vat, then for all practical intents and purposes, P is 0, or incredibly close. At the other end of things, what if we have just picked out the only 60 jelly beans in the vat that are not licorice? So millions minus 60 divided by millions, pretty much the entire vat is licorice, and P is 1, right? So if it's certainty you're after, from this sample we can conclude with certainty that the proportion of jelly beans in the vat which are licorice is somewhere between none of them and all of them, 0 and 1. And guess what? You didn't have to pick 100 jelly beans to know that, right? I hope. So from a simple random sample of 100 jelly beans, we can conclude with certainty exactly nothing. And that is always true when you're sampling, because remember, samples don't take a bite out of populations. If they do, you've got bigger problems. So my estimate, 40% of what I looked at were licorice. So bearing in mind that statistics estimate parameters, loosely speaking, I'm estimating that 40% of the whole vat is licorice. But how reliable is this? Well, again, like I said, you have no idea whether this is a typical sample or not. It probably is a typical sample. That's what typical means. But it may not be. So logically, before you can conclude what 40 out of 100 jelly beans, before you can know what 40 out of 100 jelly beans allows you to conclude, the logical question to ask yourself is, how different from 40 licorice is another sample of size 100 likely to be? So you see, it's all about the standard deviation, right? It's all about the pattern of randomness of a sample of 100 jelly beans. Here's what it did this time. How likely is it to give you something very different next time, and so on and so on. The sample you just have, the extent of the useful information you can get out of the sample you just had, is precisely as much as the answer to the question, how different is another sample of that size likely to be? It's no good having 40 out of 100 licorice on this sample if the next sample could give you 80 out of 100 licorice. Why are we using 40%? Why not 80%? You see the problem? So what do we know? We know from section 8 that for samples of size n in general, is 100 in our case, we know that for large n, and we'll say 100 is large, we had our little conditions there, but we'll assume that they're satisfied. It's hard to know without knowing what p is, but loosely speaking, we have a large sample, so the statistic is probably normal shaped. That's what the whole middle part of the course comes down to, right? So for a large sample, the pattern of randomness for the proportion of licorice we are likely to get, our p hat happens to be 40 divided by 100, but now we're talking about a generic sample of size n, or a generic sample of size 100, where the sample is still in our future, right? Then what the sample of 100, or n, jelly beans is likely to be, its pattern of randomness. We know for large n that it's normal shaped. We know that it centers around p. That was our formula. That was its mean. That was the mean of p hat. The mean of p hat was p. Remember, p hat is the arrow, p is the target. So all we're saying is there's no bias. The shots are centered at what they're aiming for. And the standard deviation of p hat, remember, was the square root of p times 1 minus p over n. Now for short, let's call that what it is. It's the standard deviation of p hat. So I'm just going to abbreviate it temporarily because we're going to be using it over and over again for the next paragraph or so. So there's nothing new here. A sample of 100 jelly beans is approximately normal shaped, centered at p, with standard deviation square root of p times 1 minus p over 100, and so forth, whatever n is. So what do we know? Among other things, we know from the 68, 95, 99.7 rule, or the empirical rule, we know that if we go two standard, whenever anything is normally distributed, we know that if you go two standard deviations to either side of the mean, you get 95% of the stuff, right? But in point of fact, that was a little rounded, right? So if you have 95% of the area in the middle, then that leaves 5% for the tails, which is 2.5% for each tail, right? And that, in fact, is an exact entry on the chart. We say 2 standard deviations, but it's really more like 1.96, right? So again, 95% in the middle leaves 5%, 0.05 for the tail. Divide by 2, 0.250, 2.5% for each tail. And the z that corresponds to that is negative 1.96. So we say 2, but I also said when we first did it, it was a little bit rounded. It's really more like 1.96. So if we go 2 standard deviations to either side of the center, or more accurately, if we go 1.96 standard deviations to either side of the center, then we cut off the middle 95% of the stuff. Well, what is the stuff? It is the random thing in question. It is the p-hats that result from different samples of that size. So again, to say that p-hat is approximately normally distributed, now the approximately again is not our problem. P-hat is approximately normally distributed with mean p and standard deviation this guy. That is to say that that is the case, is to say that 95% of all possible p-hats, remember, you can think of this as either the pattern of randomness for the p-hat that you're likely to get, or probability being what it is, how all possible p-hats from all possible samples break down into a pattern. As always, the one is exactly what we mean by the other when it comes to probability. So 95% of all possible statistics, p-hats, from all possible samples of that size are within 1.96 standard deviations of p. So the p-hats are bouncing around that center of p, no bias. And z, remember, is a number of standard deviations. So 95% of all possible, whatever the random guy is within 1.96 standard deviations of where it's centered. So this is just our basic understanding from section 3 translated for this notation. Well, what do I mean by a standard deviation? I mean the standard deviation of the guy in question, which we're abbreviating sigma of p hat. So I'm just going to restate what I just stated above. I'm just going to keep restating it until it says what I want it to say. 95% of all possible p-hats from all possible samples of size n are within 1.96 times the standard deviation, his p-hats, of p. So 95% of all possible statistics are within highlighted distance of p. Now again, what is probability? To say that 95% of them satisfy a condition is the same, this is what probability means. To say that 95% of all possible statistics satisfy a condition is to say that there's a 0.95, there's a 95% chance that our statistic satisfies that condition. If 95% of all possibles whatevers satisfy a condition, then there's a 0.95 probability that our whatever is going to satisfy a condition. Now again, remember when we're talking about the pattern of randomness, we're talking about a generic sample of size n, or whatever, in our future. So there's a 0.95 probability that the statistic we're going to get from the sample we're about to do will be within this distance of p. But again, if A is within 5 miles of B, then B is within 5 miles of A, and A and B are within 5 miles of one another, right? So let's turn it around. There is a 0.95 probability, caveat, that RP is within, there's a 0.95 probability that P, the actual truth of that, is within that distance of what we have just gotten. Now the sample is in our past, you see. So there's a 0.95 probability that the thing we're looking for is within a certain distance of what we're using, the result of our sample, the 0.4, the 40 divided by 100. Now again, the caveat on this is that there is no probability that P is anything. There's nothing random about a real world fact. What is random was the sample, right? What was random is what we were. What was random is what we did happen to get, past tense. So you do have to be a little careful. It's more technically accurate to say that the statistic probably was going to be close to the unknown truth. But informally, we can say that the unknown truth is probably close to what we happen to have. And again, that caveat is all spelled out here, and we've talked about it many times before. More accurately, there's nothing random about P, which is a real-world fact. The proportion of licorice in the vat is what it is, whether you know it or not. To be random means you can repeat and get a different result. You can't repeat with a different vat and get a different proportion of licorice in the vat. You can repeat with a different sample of 100 and get a different P hat. So more accurately, the P hat that we just got probably was going to be close to what P really is. If we're being accurate, if we're being philosophically accurate about this, it is the thing we happen to be working with which was random, and the thing we don't know, which is what it is. This is what makes inference philosophically weird. Nevertheless, we'll just push ahead and go on. There's a 0.95 probability that our population fact is within set distance of our P hat. In other words, it is probability-wise, it's within this distance of P hat. In other words, what does it mean to be within this distance of P hat? It means that you can be as much as that minus that subtracted from P hat, or that added to P hat. So there's a 0.95 probability that P is between P hat minus that distance, sigma P hat, and P hat plus that distance, P hat plus sigma P hat. And while we're at it, let's de-abbreviate. So there's a 0.95 probability that the thing we don't know is within that distance, added or subtracted, that distance to either side of P hat. And if you actually want to formulate it, you can just create the low end and the high end by actually subtracting and actually adding. You see it both ways. You see it in this kind of a form, and you see it in this kind of a form. But strictly speaking, this is the confidence interval. We have actually subtracted it to get the low end and actually added it to get the high end. Now, again, we say plus or minus in common parlance, right? But really, minus the low end is what comes first, and plus the high end is what comes second when you're writing it down, right? So there's a 0.95 probability that P is between these walls, which we can theoretically compute. Theoretically. But again, there is no, technically, if we're being 100% pedantic about it, there's no probability of P being anything. So we talk about confidence instead. We are 95% confident. We are 95% confident that P is between these numbers. Now again, what it really means in the real world to be 95% confident of something remains to be seen, and we'll talk about it. But the bottom line is, if you fill in all these blanks, you've got a 95% confidence interval. This is what makes inference difficult to think about. It's probability done backwards. You're reasoning from the sample result you happen to get, but you could just as easily be gotten something else to what the population fact, the parameter, really is. Hence, when we talk about what population facts are, we don't talk about what they probably are. They're not probably anything. We talk about what we're confident about. So, to be technically accurate about it, what we have is a confidence interval, specifically a 95% confidence interval for P. We are 95% confident that P is between, well, compute the numbers. What does it actually mean in the real world? So we take a sample, we get some walls, and the bottom line is that the population fact, which is what it is and can't be something else, is either between the walls or not between the walls. Now, let's elaborate on that a bit. Remember, at the end of the day, we're never going to be certain about anything. We take a sample, we get some walls. End of the day, the population fact, the parameter, is either between those walls or it's not. End of story. However, how does this play out? If we got a typical sample, if the sample happens to be close to what the parameter is, then it's between the walls. On the other hand, if we got a sample, a statistic that happens to be very unusual, then the truth is probably not going to be between the walls. Let's think that through. If we have just picked out the only 40 licorice in the entire vat, then our p hat is 0.4 and our p is effectively 0, and they're not remotely close to one another. Or at the other end of things, if we've just picked out the only 60 non-licorice in the entire vat, then our p hat is still 0.4 and the p is 1, and again, they're not remotely close to one another. And the confidence interval you generate is the walls you generate from that sample are not going to contain p. So you see how this plays out. On the presumption that our sample is relatively typical, the walls that we generate will contain the truth. On the other hand, if our sample happens to be very unusual, then the walls it generates will not contain the truth. So there's no guarantees. Remember, without knowing p, and that's the whole point, you have no way of knowing whether this sample was typical or not. But it probably is. That's what probability means. And it is unlikely that it's not. Again, that's what probability means. So when I say typical, what do I mean? Well, in our case, among the 95% most typical. When I say unusual, what do I mean? Well, in our case, among the 5% outlying, the 5% most unusual. So at the end of the day, one of two things is true. Either our sample is among the 5% most extreme samples we could have gotten, in which case p is not between these walls, or it's among the 95% most typical, most central, in which case p is between these walls. Another way you can say it is you can say that 95% of the p hats that we could, 95% of the p hats we could get, 95% of the samples we could do, 95% of the confidence interval walls we could generate will contain p. So yeah, if you happen to get a very unusual sample, then obviously all bets are off and your estimate is going to be useless. But again, by definition of unlikely, you probably didn't get a very unlikely sample. That's what it means to be unusual, right? You probably didn't just get one. Provided our sample is among the 95% most common, most typical, most central. Remember, this is roughly normal shaped, it's symmetric. So 95% in the middle, 95% peeking out there, 95% most common, 95% most typical, 95% most central. They all mean the same thing, right? We're talking about that 95 area in the middle. If the sample we just got was among the 95% most typical we could have gotten, then the walls you generate will contain the truth. If it happens to be one of the 5% outlying samples, tail, tail. If it happens to be one of the 5% outlying samples, 2.5 either way, 5% outlying, then the walls it generates will not contain p. That's what it means to be 95% confident about something. We'll summarize it as we go. Maybe I should say it one more time. One of two things is the case. Either the proportion of licorice in the vat is between these walls, or it's not. But if it's not, it's because the sample you happen to be working with happens to be one of the 5% most unusual samples you could have gotten. Again, you probably didn't just pick out 100 jelly beans and get the only 40 in the entire vat. That would be like the most extreme sample you could possibly get. And you could get it, and the walls that you generate and the statistic in general could be useless. But you probably didn't just get that, right? You probably didn't just get the most extreme sample you could possibly get when picking from millions. That's what extreme means. So where do we leave off here? Either the proportion of licorice in the vat is between the walls or it's not. But if it's not, it's because the sample you happened to be working with happens to be, through sheer bad luck, not bias, just through sheer bad luck, one of the 5% most unusual samples you could have gotten. You could pick out a sample with no licorice, even though half the vat is licorice, and so forth and so on. There are never any guarantees, but the larger the sample is, the harder it is to pick unbalanced and unusual one, right? That's just a consequence of what it means to amalgamate more and more sample elements into a bigger and bigger sample, right? In other words, the larger the sample is, the more likely it is to be representative of the vat, the harder it is to be very unusual. If you happen to pick a very unusual sample, any confidence interval, and indeed any conclusions whatsoever that you get from that statistic are going to be useless. But you probably didn't. That is what unusual means, right? So there is a brief course in what it means to be 95% confident of something. We have a bigger problem. Let's see. So let's go back up here, I guess. Let's go back to square one here. We don't know what P is. We don't know what the proportion of licorice in the vat is. We have just picked out 100 jelly beans and 40 of them are licorice. So N is 100. P hat is 0.4. 40 divided by 100. That's where we stand. N is 100. P hat is 0.4. P might be anything. We're trying to estimate it. That's what we've got to work with. And now we'll compute a 95% confidence interval for P. Actually, let's go to this one. It's a little easier to look at. So all we have to do to get a 95% confidence interval for P, all we have to do is fill these blanks. Okay, ready to go? P hat was 0.4. N was 100. What was P? This is more fun to do by a show of hands in class, but the bottom line, of course, is that the whole thing has been a colossal waste of time, right? If we knew P, we wouldn't. If we were capable of filling these blanks in order to estimate P, then we would know P and we wouldn't need to estimate it. Did you get that? Let me say it again. The whole reason we're getting a 95% confidence interval for P, the whole reason we're estimating P, is because we don't know what it is. If we knew P, we wouldn't have to estimate it. And the only way we can estimate it is by filling these blanks, well, in particular, these blanks. So you have to know what P is in order to estimate it. But if you knew what P was, you wouldn't have to estimate it. So the whole thing ends up being a colossal waste of everybody's time. Almost. Now here's where the magic happens. Let's see. So, well, let me just put it this way. Let's go back up here. Stay here for a second. And so there's our confidence interval. And again, if we could fill those blanks, we wouldn't need to estimate P. We would know what it was. Now, the following has no reason to work. And if you have any sense of logic about you, it should strike you as very dubious. But it actually does work for reasons we'll discuss. We don't know what P is. Therefore, we are incapable of filling these blanks. However, we do have an estimate for P, and that is P hat itself, the 0.4, 40 over 100. So in the absence of knowing what P is, let's put in our best guess for P. our only guess for p, which is p hat, 0.4 times 1 minus 0.4. And then, since p and p hat are probably close together, the resulting computation is probably close to a 95% confidence interval. In other words, it is, if we use p hat instead of p in these blanks, then what we have is our estimate of a 95% confidence interval. Now, if that strikes you as reasoning in a circle, p hat is close to p, therefore p is probably close to p hat, therefore p is probably close to p hat, then congratulations, you've got a good sense of logic. But the reason it works is the following. Now, I grant you, p and p hat are not going to be the same thing. You know, you're not going to flip a coin a million times and get 5, 0, 0, 0, 0, 0 heads. It's 2 on the nose. So there is a difference between what p is and the p hat we happen to get. That's the whole point of all of this. But for a large n, it's probably not that much of a difference. Now again, if that still strikes you that we're reasoning in a circle, let's say for the sake of argument that p hat, as we said, was 0.4, but really 45% of the vat is licorice, so the p is 0.45. Well, 0.4 and 0.45 are not terribly close together. But when we divide them by 100, or 1,000, or a million, or, well, a million's a bit much, but when we divide them by a very big sample size, you see 0.4 and 0.45 are relatively far apart. But divide them by 100, and now they're a lot closer together. So it is the dividing by n. Remember, practical samples are large anyway. So if you divide by something large, then this guy is a lot more, in fact, the whole guy. This guy is a lot more like his counterpart with p hat than p and p hat are like one another. Let me say that again. This guy, what is this guy? What is this highlighted guy? The standard deviation of p hat. That guy and the corresponding guy with the p hat in it, square root of p hat times 1 minus p hat over n. Those two guys are a lot more similar to one another than p and p hat are to one another because of the power of dividing by a large n. And that is what makes it not reasoning in a circle, and that is what makes the whole thing actually work. Put a p hat on this guy, and what we have is an approximate 95% confidence interval. And because it would be totally self-defeating to fill in the blanks in what you're actually seeing here in order to estimate p, we promptly forget about the approximately and just get on with our lives. And we take that inevitable fudge factor for granted. Now, with all that in mind, here are some of the jargon and technical details. The standard deviation of p hat, the statistic in question, is the square root of p times 1 minus p over n. Now, anytime you are forced to estimate the standard deviation of a statistic because you have no way of knowing what it is, and obviously, if you ever needed the standard deviation of the statistic we use to estimate p, then you would not have p. So it would be totally self-defeating to know this highlighted thing to the goal of trying to find p. The fudge factor is inevitable. The name for the fudge factor is called standard error. Anytime you have to estimate the standard deviation of a statistic by using sample information where population information is really called for, it's called the standard error of the statistic. It's not terribly important for this section. It's just a formula that we absorb and move on. But it will be very important when we get to section 18. So I'll say it one more time. Anytime you are forced to estimate the standard deviation of a statistic by putting sample information where population information, the corresponding population information is really called for, it's called the standard error of the statistic. So just stare at this for another second or two. This is the standard deviation of our statistic, p hat. And this is the standard error of our statistic. The same guy with a hat in it. And I think that's what I say down here. Whenever you have to approximate the standard deviation of a statistic using sample information where population information is really called for, the resulting approximation is called standard error. The standard error, the highlighted thing here, is my estimate of the standard deviation of the statistic. My estimate, my guess at the standard deviation of p hat. If we put our guess into the formula where this guy was really called for, then we have an approximate 95% confidence interval. For now, it's just a necessary fudge factor. Again, if you knew p hat, you wouldn't be looking for p hat, so you can kind of just forget about it. But it will be important in section 18. So if this seems like circular reasoning, p hat is probably close to p, therefore p hat is probably close to p. Note that we're dividing by n, which means again that these two guys are much more similar to one another than these two guys are, and that's what makes it work. The larger the sample, and there's all kinds of reasons you want samples to be large anyway, the more similar these guys are to one another, even if these guys aren't particularly close. So that's what makes it actually work. Now, we promptly forget about the approximate because it is inevitable. It is just unavoidable. But remember it for the future, or keep it in the back of your mind that there is this fudge factor in the formula. An approximate 95% confidence interval for p is p hat plus or minus z times the square root of p hat times 1 minus p hat over n, where for the 95%, the z is the 1960. Now remember, that's where we started. If you wanted 95% in the middle, then it was 196 to either side. So it's the 95 that gives you the z. We can do other confidence intervals, and we'll do them later. So p is probably close to p hat. How probably? 0.95. How close? This close. Try again. Try a third time. Try a fourth time. Anyway, this guy. The thing after the plus minus. That's how close. I'm not having too much luck encircling that precisely, and I'm having even less luck highlighting it. I think it's the text box. There you go. Perfect. So there is how p hat probably was going to be close to p, to be more precise about it. How probably? 0.95. How close? This close. So this is what we call the margin of error of the confidence interval. We're 95% confident that p is this number with a margin of error of this number. It looks something like this. Remember that the confidence interval is going to be double the margin of error, or if you want the other way around, the margin of error is going to be half the confidence interval. So the entire confidence interval, here's our statistic, here's our p hat, subtract the margin of error, you get to the low wall. Add the margin of error, you get to the high wall. This will work for this visual aid will work for any confidence interval, but in our case, the statistic is p hat, and the margin of error is z times the square root of p hat times 1 minus p hat over n. So hence in our example, we're good to go. A 95% approximate, of course, we promptly forget about that. A 95% confidence interval for p is 0.4 plus or minus. Our z is 196. Our p hat is 0.4. This therefore is 0.6. This is 100. Good to go. After that, just watch the order of operations and watch the general smallness of this square root. Remember, any sample worth its salt, any sample big enough to be interesting, this is going to be very small, right? Typically 0.0 something or 0.00 something. So watch the rounding. Be very careful. But without any internal rounding, that would be, let me just do it on my calculator really quick. I'm sure it's right. 0.4 times 0.6 is 0.24. Divided by 100 is 0.0024. And the square root of that is 0.0489897949. Call it 049. Sorry, what happened? Oh, yeah. 0.0489897949, and then I'll multiply it by the 196. That's what you don't want to forget. And now what I'm getting is the 0.09601999979. Well, bottom line, 0.096. So what are the various ways we can say this? We are 95% confident that the proportion of licorice in the vat is 0.4 with a margin of error of 0.096. Say again, we are 95% confident that the proportion of licorice in the vat is 0.4 with a margin of error of 0.096. Or you can actually subtract it and add it and get the actual confidence interval. So if we subtract it, we get 0.304. If we add it, we get 0.496. So we are 95% confident that the proportion of licorice in the vat is between 0.304 and 0.496. It sounds almost silly when you say it with percents, right? We are 95% confident. We're not even positive. We're only highly confident that between 30% and 50% of the vat is licorice. Now, bear in mind, we could do better than that with our lying eyes, right? The licorice ones are not hard to find. They're the black ones, right? So remember I said that the vat was totally sealed, totally opaque, and we had no visual impressions whatsoever? Even with all the jelly beans mixed together, with our lying eyes, we could probably do better than somewhere between 30% and half the vat, right? Well, I never said that this sample was going to be useful, only that this is what you can conclude from 100 jelly beans. From 100 jelly beans, we're 95% confident, we're not even positive, that between 30% and 50% of the vat is licorice. Well, just for verbal purposes, don't round more than you're told to round. Now, logically, a larger sample is probably going to be closer to the truth. Remember the taller, thinner bells that we get from a larger sample centered in the same place, which means that the sample result is probably not as far away as a smaller sample would be. So a larger sample means that you're more and more likely to get something that close to the truth, and vice versa. So logically, a larger sample will vary less. Large sample, less variability, and result in more precision. But how does it play out in formula terms? Well, you can see it, right? The larger n is, the smaller you're dividing by it. So the smaller this whole square root thing is, which is not going to happen. What if I start here and use the keyboard? Oh, that didn't work. No, I lost it entirely. Oh, here it is. So anyway, the larger n is, we're dividing by it, so the smaller this guy is going to be. And then we multiply it by a specific z, and again, the larger n is, the smaller number you're going to get here, the more you're dividing by. So the larger n is, the smaller the margin of error. You can see it right there in the math. It's the n in the bottom that makes it work. Remember I told you in sections 8 and 9, take special note of that n in the bottom because it was going to be important. Larger sample will bring down the standard deviation of the statistic, and or in our case, the closest thing we got, and therefore the entire margin of error of the statistic, which again I'm going to have no luck highlighting. There it is. So the more we divide by, the larger n is, the smaller this is. Well, we can see it. For the sake of argument, now let us say, simply for the purposes of comparison, that we took out 1,000 jelly beans and 400 of them are licorice. Let me pause there to add that if you pick out 900 more jelly beans, you're not going to get the same p hat, right? Solely for purposes of comparisons. All other things being equal, 40% of our sample was licorice, but it came, for the sake of argument, from a bigger sample. So it's contrived, yes, but just to have a comparison. What if that 0.4 statistic was the result of a larger sample? Well, the bottom line is that you've got something bigger on the bottom line, right? You're dividing by 1,000 there. Let me just do that really quick. 0.4 times 0.6 is still 0.24. Divided by 1,000 is scientific notation. 0.00024 looks like. Square root of answer, anyway, is 0.01549 something. And then if I multiply it by the 1.96, it goes from 0.154919334 to 0.0303641,894. Well, call it 0.030 because I seem to be using 3 decimal places for no particular reason. So now from a sample of size 100, we have a margin of error of 0.96, almost 10%. From a sample of size 1,000, we get that margin of error down to 0.030, 3%. Now your lying eyes is probably not going to be able to peg it down to somewhere between 37% and 43% of that being licorice. So a sample of size 1,000 is actually useful. We're 95% confident that the proportion of licorice in the vat is between 0.4 minus 3 and 0.4 plus 3, 0.37 to 0.43. This is actually useful, unlike the previous sample. 1,000 jelly beans will allow you to conclude that you have somewhere between 95%, a sample of size 1,000, sorry, I'm reading while I'm talking. A sample of size 1,000 will enable you to conclude something reasonably useful, a margin of error that's actually useful. Now we're 95% confident that 0.4, the proportion of licorice in the vat is 0.4 with a margin of error of 0.030. Now again, you see it both ways. You see it in center radius form. This is the way a journalist would say it, right, if he knew what he was talking about. 0.4 with a margin of error of 0.303. That's the way you read it in the newspapers, if there are still newspapers. But this is the actual confidence interval. Go the extra mile to subtract it and add it. You want to get used to seeing it both ways. But strictly speaking, go the extra mile, actually subtract it and add it, and you've got the actual confidence interval. That being said, again, people sometimes say it this way, right? Estimate with margin of error of whatever. Now, this doesn't really apply to us because I didn't physically photocopy normal charts and hand them out to everybody in class. But at the top of the sections where it is used, in particular section 10 and section 12, you will find this little confidence row. Now again, we have some encoding issues here, which are probably not going to be easily fixed. If I go to Western encoding, there you go. So that'll get rid of those quote problems. So at the top of the various sections where you'll need it, you see this confidence row. What this does is it, number one, prevents you from having to do it yourself. Like I said, 95% in the middle is 0.5 in the tails. Divide by 2, half for each tail. And if you look up the 0.250, you get the 196. So this prevents you from having to do that, and while we're at it, it gives you an extra place after the decimal. So in this is all to do with the normal chart. This is solely the normal chart. Nothing to do with jelly beans or p-hats or proportions or formulas we're talking about at the moment. This is just the way the normal chart works, right? If you want 90% area in the middle, 10% in the tails, 5% in each tail, then you go 1645 to either side, negative 1645 to positive 1645. If you want 99% area in the middle, 1% in the tails, 0.5% in each tail. Well, look it up and you'll see it's somewhere between negative 257 and negative 258. So if you go positive or negative z of 2.576 in either direction, you get the middle 99% of the area. And again, that's solely to do with the normal chart. So it is here again if you need it. So it doesn't necessarily have to be a 95% confidence interval, you see. Now I'm not going to ask you any that are not here, so you can just use this as a reference. It'll save you always having to work it out yourself. So in general, it is the confidence level that gives you the z. If you want 99% confidence for interval, then for instance, then this is going to be 2.576. If you want an 80% confidence interval, then it's going to be 1.282. Now, anytime you're talking about normal distributions, z's, that's the case. So let's go the other way. Let's go back to our sample of size 100. If we wanted a 95% confidence interval, then that's how it plays out, a margin of error of 0.96. What if we want a 99% confidence interval? Well, even before we run the numbers here, let's think it through logically. The more confident you want to be that the truth is between the walls, the further apart the walls are going to have to be, right? So if you want to be 80% confident, then you can have the walls relatively close together. But if you want to be 99.9% confident, then the walls are going to be much further apart. So that's the other point here. The first point we made was that the larger the sample size, the smaller the margin of error. Common sense, larger samples allow for more accuracy. But it's also common sense that the higher the confidence, the wider the margin of error. The bigger number the margin of error will be, the wider everything will be. So the more confident you want to be about where it is, the larger space you're going to have to give it to live in. So if we actually run the numbers, again, compared to I'm going back to the original sample of 100 now for purposes of comparison. So the n of 100 and p hat of 0.4, 95% confidence, margin of error is 0.96, 0.304 to 0.496. By way of comparison, if we crank it up to 99% confidence, and of course this would be 1,000, so there is a typo. That's what happens when you cut and paste. I'll just make a note, 99% confidence. I'm not going to be able to fix this for a very long time to come because I have to be in my office to do it. But I'll make a note online. Oh, no, sorry, my mistake. We are doing the sample of size 100. We're good. So, to recap, sample of size 100, but if you want 95% confidence, then margin of error 0.96, low wall 304, high wall 496. And if you want 99% confidence, then this is exactly the same number it was before, but now you're multiplying it by something bigger. Remember, more area in the middle means a more extreme z, right? More positive, more negative, bigger number. So that cranks it up from 0.96, 9%-ish, to 0.126, 13%-ish. So the low wall is even lower and the high wall is even higher, right? Subtract the 126 from the 0.4, add the 1.26 to the 0.4. Instead of a low wall of 304, we now have a low wall of 274. Instead of a high wall of 0.496, we have a high wall of 0.526. This is even wider than our original 95% confidence interval, which, by the way, was pretty useless. So under the circumstances, a higher level of confidence would be a silly thing to demand, but nevertheless. So here's where I summarize that, basically. Now again, I don't seem to have summarized this nicely in any one place in the notes. So let me just say it verbally. The various ways of, I just want to pick an answer here. Here we go. The various ways of stating this. Number one, we are 95% confident that the proportion of licorice is 0.4 with a margin of error of 0.096. Number two, a 95% confidence interval for the proportion of licorice is 0.304 to 0.496. Number three, we are 95% confident that the proportion of licorice is between these numbers. What am I up to? Number four. Provided our sample happens to be among the 95% most typical we could have gotten, the proportion of licorice must be between the walls. Say again. Provided our sample happens to be among the 95% most typical, most central, most common we could have gotten, the truth, the population fact, the proportion of licorice in the vat must be between the walls. What am I up to? About 5? Unless our sample is among the 5% most unusual we could have gotten, the proportion of licorice is between these walls. Unless our sample happens to be among the 5% most unusual, most atypical, most uncommon, most extreme we could have gotten, the truth is between the walls. If the truth is not between the walls, if the proportion of licorice in the vat is not between the walls, then it is because our sample happens to be among the 5% most extreme we could have gotten, right? One of three things is the case, right? Either the proportion of licorice in the vat, which is what it is between these walls, or it's not. If it is, it's because our sample happens to be among the 95% most typical we could have gotten. If it's not, then one of two things is the case. Either this particular sample has an abnormally high amount of licorice in it, and we're overestimating the whole thing, and the proportion of licorice in the vat is really over here someplace. Or this sample happens to have a weirdly low amount of licorice in it, and we're underestimating the whole thing, and the truth is really over here in 0.5-ish whatever territory. But put those last two things together, and there's only a 5% chance of that happening. There's only a 5% chance that the sample, by definition, there's only a 5% chance that you are going to get one of the 5% outlying samples, meaning that the walls you generate will not contain the truth. So if the walls you generate do not contain the truth, it's because you're dealing with one of the 5% outlying samples. 2.5 lowest you could have gotten, in which case the truth is really over here, or 2.5 highest you could have gotten, in which case you're overestimating the whole thing and the truth is really over here. But again, put those last two things together. There's only a 5% chance you were going to get a sample that would result in walls that did not contain the truth. Okay? Various ways of saying this. Now, this is getting to be on the long side, and we have one more point to cover here. So I think I'm going to stop it here, and we'll pick up this PS about minimum sample sizes in the second part of this video.